老师我忘记了，我下去拿一下。
Not so many students show up today. Okay, so our class is gradually becoming like private tutor. Yeah. 快变成家教班了。It's okay. Yeah. As I said at the beginning of the class, I don't take attendance. So if anyone can study this material without coming to the class, it's perfectly fine with me. Yeah. So as long as you can, fully understand the material, there are more than one way to learn. So, but before we start the class, okay, one thing to talk about, like got the email from a student saying like they would like to extend the deadline of this homework because like there are other homeworks from different subjects that have like similar deadline. I know like we don't have a lot of samples. We only have 5 samples here now. Is it the case? 所以说这个不是期末那个第3次作业这个 deadline 不是，我记得是这个周末。对，但是好像有学生讲说，好像有别的科目刚好也是这个时机会是这个 deadline 啊 ，always。所以 so that student actually requested like to extend like 3 to 4 more days. Okay, so I will extend 3 days. Is it okay? I hope that it helps. Okay. 就是那个，帮我把那个homework 3的 deadline 延长3天。
好。
哇，你在那个class 上announce一下，然后把那个就是 deadline 延长3天，调一下那个设定，好不好 ？Okay. So come back to the class. Okay. So last time we talked about the shortest path algorithm. Okay. That algorithm assumes there is no negative weight ages. Okay. And the performance, I mean, actually, if you look at that algorithm, like very closely, it is similar to minimum spanning tree. Okay. And the time complexity is pretty much the same as the one in the minimum spanning tree as well. Okay. But that was, of course, because of the assumption, okay, where like there's no negative weight cycle, negative weight like ages. Okay. But we know if there's a negative weight cycle, then some shortest path may not exist. This is obviously the case. Okay, because I recall this very last time. Okay, so this is very clear. If this is a very cycle, from YouTube you can have as low of path as you want. Like you want the even lower weight path, which is like run through the cycle, few more times, and you will get it. So there's no definition. You cannot define shortest path for you to be in a case like this. Okay. So, but it doesn't mean. It does not mean if you have negative weight age, your graph does not have shorter paths, right? Yeah, these are 2 different things. Okay, I mean it's okay for the graph to have negative weight ages, but has no negative weight cycle, right? So that's the first thing. The second thing is we also want to know, okay, if you have a graph, okay, how do you determine if there's a negative weight cycle? That's another valid question to ask, right? 就是你现在第一个说有那个有一些 age 它的位是负的，并不代表一定有负的 cycle， 所以这些 shortest path 可能还是存在的，所以你要怎么找它？第二个是说， 如果你的 graph，我给你一个 graph， 你要怎么样子很快速的找说这个 graph 没有或者没有 negative rate cycle， 所以so that's why there's another shortest path for building for. Yeah. So building for algorithm, like the setting is similar to the previous algorithm that we talked about. Like the previous algorithm, shortest path algorithm was the name is extra. Okay, I think I mentioned about this guy last time. Is well, I mean, if you are, you know, if you are into like the state of Texas, I mean, he helped like Ricky Austin a lot, okay. But anyway, so the building for algorithm, it deals with similar question, similar problem with a different assumption. Okay, you will find all shortest paths. Then, from the source S, okay, to all other nodes. Okay. Or it could be used to determine a negative rate cycle. So, I think in our previous discussion, we mentioned that this building for was actually taught in your data structure class. Is that right? 你的资料结构有教过 extra， 有教过 building for， 是不是？是吗？张副院长会非常伤心。Okay. Anyway, now we will talk about it today because like previously I was thinking we will focus more on the proof as well as the extension of the for example like how it can be applied to solve like some other interesting problems. But anyway, yeah, so this is building for errors. So again, it is similar to so I previously mentioned the extra similar to Williams chemistry. So now this one, okay, in some sense it's also similar to extra, but it has some special parts. Okay. So initialization, this part is exactly the same as extra. Okay. And then we start from any node, not S, okay, not S. Okay, and we will do the relaxation for every age, and so up to the end of the relaxation part. They're slightly different, and they're slightly different than extra, but not enough. And the following part is used to detect if there's a negative rate cycle. Okay. So let me put it this way. Okay. So it's like this. If there's no negative rate cycle, your algorithm is supposed to converge kind of relaxation steps. Like after you finish the follow, the second follow. But okay, in the third one, okay, I mean the third follow for each age, okay, you okay, you do this once more. If you are able to reduce the weight of any path, at this moment, it means that there's a negative weight side. Okay, because the shortest path should have been found. It is not supposed to, you are not supposed to reduce the weight anymore. If it is the case, you have a mental weight side. Okay. So, the first initialization, obviously, is a big O B, right? Big O B. The second, the third one, okay, the third loop is obviously bounded by the second loop. So the complexity is, is primarily contributed to from the second loop. Okay, and this second loop is very simple. Okay, for I, okay, from 1 to b minus 1. Okay, so the outside whole loop is like it runs like b minus 1 times. Okay, and inside, okay, regardless, you try every age. Okay, you try every age. This is also like the primary difference. In the bilateral algorithm, we do not try every age for the relaxation, but here, okay, we try every age. Or let me make it more clear. Okay, we try every age with a fixed order, because like the ages are stored in your set at E, okay, in a certain order, right? So yeah, you try this relaxation for every age, but it's like this is a certain order. That order really is not that important, but it will become important later on when we talk about another version of this. Right? So, because it's a simple, you simply try every age, okay? For every node. Okay, so the complexity is obviously b times e. Okay. So, the example, to give an example of the overall, you can see that in this graph, we have like several ages to be exact. 1, 2, 3, 4, 5, 6, 7, 8. We have 8 ages. We have 5 nodes and 8 ages. Okay. And 2 of them are negative. Okay. From A to B is -1. From E to B is -3. Okay. And these ages, as I said, they usually are stored in a certain order. So we first initialize. Okay. We start from node A, and all the other nodes are initialized as input. Okay. And then those like small numbers indicate the order of the relaxation that we that, for example, we'll go to the H from B to E first, and then we try H from B to D, and then we try the H from B to C, and then the fourth one is the H from A to B, and the next one is H from A to C, and so on. Okay, so those are small number, okay, in black, okay, in color black, indicate the older those ages will be, will try the organization. So first, obviously, try the first one, okay, from B to E. Okay, so relaxation, what is relaxation? Basically, okay, if the dB greater than du plus WUV, then dB will be updated the variable dB component. So here, we try the first one. So you will see that D, in this case, it will be DE, okay, which will be infinite. Infinite is not greater than dB plus the H with 2. Okay. Well, it's infinite, most likely. So nothing needs to be modified. Okay. Actually, relax it. Nothing needs to be modified. They are both infinite. Then we try the second, which is this one. Okay. So H from B to E. And again, for a simple reason, there's no need to modify the H. Okay. The third one is from B to E. Again, nothing will be changed. The fourth one is the different story. Okay, because here, okay, the original distance dB was infinite, right? dB was infinite. The infinite is greater than dA, which is 0, plus negative 1. Okay, so the total is negative 1. So negative 1 is smaller than the infinity. So we update the variable dB to the negative 1. Okay, and we do this for the fixed H. Okay, again, for similar reason, we will update the EC to be 4. BC was originally even, and even is greater than 0 plus 4, so it's becoming 4. And then we try the number 6 H. Well, it's from B to C. Well, 4 is not greater than infinite plus 5, so nothing will change. Okay, and then number 8 H. So number 7 is H. Here. Okay. So this one, okay, is interesting. Okay, because that previous, the DC was already updated before. But now, okay, after you try the H from B to C, because the dB now is negative 1 plus 3 is 2. 2 is smaller than 4, so we have to update DC to be 2. Okay. Okay. And then this is the 7th H. 8th H from E to D, nothing to be done. So we are done with the first pass. We are done with the first pass. Then so that's the end of the first pass. So we will do this. We have 5 notes. We will do 4 rounds. 4 rounds. We'll do these 4 rounds. Okay. The second time, again, we try the first stage. Okay. So E will be up, the DE will be updated because the name 1 plus 2 will be 1. Okay. And then sixth one. So it will be 1 plus 5. Well, so nothing will change. The sixth one, seventh one, then 1 plus 3 will nothing will change. Eighth one, okay, is 1 plus negative 3. So it's negative 2. So it is lower than 1. So we'll update each value to negative 2. Okay? So that's the end of the second path. But now actually it's already stable. We already found all the shortest path. So we will, we'll run this path. I mean the third path. The third path and the fourth path, whatever. Nothing will be changed. Okay. So that's the final answer. So because we tried every age, right? Here we tried every age. So let me ask you one important question. At the end of the first pass, what do you do? What does this pass give you? What does each pass give you? At the end of the first pass, okay, because you already tried every ages, right? So basically, if for any two nodes, if they are neighbors from U to B, okay, you now know, like, by using one edge, the shortest path from the previous node to this node, right?就是说你现在，因为我们尝试所有的edge，对不对？所以你经过一次的 pass， 其实你是知道说，就是说从 U 到 B 好，从这两个 node， 任何两个 node， 如果他们是邻居，他们之间的那个最短的那个路径，已经走过一次，对不对？已经知道，比如说像我高三。From A to C, we know from A to C that probably that's not a good example, but let's see. Because it happens that in the first pass, because of the order, we already found like the shortest path from A to C is this one, right? It's this one. From A to B and from B to C. But if order is different, okay, say you would have found, okay, you may not be able to find this one. But you are definitely be able to find this one, right? So the shortest path, if they are neighbors, okay, if you only allow to use one edge, you already find like the shortest path. And then after the second path, the second path. That being said, for example, for this node, you know, okay, negative 2, it comes from this one and this one, right? Like, within 2 hops, the shortest path within two hops, you already found it. Between any two given nodes. If there are short paths like two hops, you already found it. Right? So that's the key idea in development code. Because okay, here we want to prove the development code like will result in the ED will report the way of short path for all the nodes. The idea is actually so simple. Remember, we talk about this problem. If this is a short path from the V0 to Vk, okay, if this path is a short path, then any part of this path must be shortest one, right? We mentioned about this, right? Because if it is not, we can replace that portion, that part, by a shorter one, which will result in an even shorter path for the whole path, right? Okay, so that's the idea. Okay, so any portion of this path must be the shortest one. Okay, so we know that the delta S to vi, so okay, vi equal to delta S to vi minus 1 plus w vi minus 1 to vi. So regardless of which place you start. And here we can kind of, this is kind of like induction. Okay. So initially, obviously, dv0, which is ds is 0. We initialize it as 0, right? That's as for initialization. So the dv0 is, suppose you don't have any negative wave cycle. Suppose you don't have any negative wave cycle. 0 must be the shortest one, right? From the node to node itself. So this must be the shortest one. Okay. So then after the first pass, through all the edges, we must be able to find, this, the V1 from the starting node to V1, right? As I say, like here, you try every edges. So from V0 to V1, this shorter path, this is only one path. We must be able to find it, right? We may be able to find more, as I said, before the other pair, but that's not an issue. That's not an issue. We guarantee to be able to find this part, right? You find the shortest path between these two. If this is the shortest path, you must be able to find it. Okay, after the end of the first pass. So after the end of the second pass, we will be able to find from V0 or S to here. Right? Based on our previous discussion. So we keep doing that. So this is kind of just like induction. So after K passes, okay, so we have the dvk delta as shows. So this is an argument. Okay, this is not very formal proof. For a core proof, you need to use induction. But induction is not that difficult. Okay? I mean, if you can accept this argument, you can easily modify this one into a core induction. But it's not done yet. It's not done yet. You may argue, how about like we have like a very, very long path, right? But now I'm telling you, if there's no negative wave cycle, regardless how you arrange your node, any shortest path, you will not go through more than, if you have n nodes, you will not go through more than n minus 1 edges. Why? Because this is a very simple, pigeon hole principle. If you start the pigeon hole principle from your discrete mass, right? So if say like if it's from S, you go through because we assume there's no negative wave cycle, right? We assume there's no negative wave cycle. So your path, the shortest path must be simple. In other words, there's no cycle in this path. But now you are required to fill in the node at each of these space, right? Because you have only n nodes, right? You have only n nodes. So, just like 指数问题，就是小时候你看指数，如果说我跟你讲说中间有五个尖，那有6颗水，对不对？对不对？这是小学问题嘛，对不对？那if you have n minus 1 edges, then you already have n nodes, right? So you already use all the nodes. Okay, if you have more edges, that means some nodes have to be repeated here, right? So when you have repeated node, that actually indicates the cycle, right? You can get rid of the cycle, suppose because again, we assume there's no, so far we assume there's no negative wave cycle, right? So that's the idea, okay? So any shortest path, the length has to be shorter than the size of d minus 1. Shorter or equal to, okay? So because of that, we run this loop, the size of d minus 1, that was 1. Okay? So we make sure, even the longest shortest path to be found. Okay? So but we're not done yet. Remember, we still have that additional few lines in the Bell 4 elements, right? So I just mentioned that at the end of size of d minus 1 loops, okay, we already found all the shortest path, right? But if you run these edges again, and is able to reduce any show this path. What does that mean? That means, if, after you run this B-1 path, if you try to run a realization on all the edges again, and you are able to reduce any EV value, that means, you have a negative weight cycle. Okay. From node S to be exact, you have a negative weight cycle from node S to that particular B node in this path. And this is the negative weight cycle. Okay? So we done with like going forward. Very quick, right? Very quickly. Okay. I hope not to spend so much time after supposedly. I know some of you may forget, at least you have our Professor Zhang is very took her time to teach you like German or supposed like a year ago. Yeah, a year ago. Yeah, but yeah, I mean I still like finish everything. I'm not trying to rush it, but I hope like it's already remind you about this material. So we need to talk about like the other thing related to the build goal, not more. Like what are the applications of the build goal? Okay, so yeah, let's take 10 minutes break. We'll come back. We'll talk about these things.
6号，对，因为最新好像是0429，那最新是上上节。
还不学了。对对对。就像这次作业我们03年代到对。
门竟然是锁的，我进不来。这个看一下发生什么事情。
然后说前面那个锁吗？
对呀、啊。
作为老师上课的老师。
Okay. So let's talk about application of neural network. Let's show this back. Okay. We know like linear program is one of the important one of the important problems in like industrial engineering. Okay. No, actually, when I was like a student, like我以前在大学因为那时候看大家都在搞研究所，对，because at that time we don't have like 没有那个年代我们没有推甄的嘛。当然，我的成绩也可以推荐，对，那他们那个GPU was so terrible, 2.74 out of 4, so that's like really no place for second. I tried like place it, but anyway, so with a lot of like classmates prepare for like radio exam. So I also try to prepare for the exam. And yet I was I got into NTHU Google with Jinsen Google. Yeah. But I quickly find that I'm not interested in that. But that's not the point. The point is that, okay, in industry engineering, okay, they have 3 branches. One branch called like operating system, one branch called like simulation, the other branch, the third branch called like stochastic, like process. So stochastic process is very theoretical actually. But they didn't, I think they didn't do it right. Okay? But of course like now they may do it much better now. I think simulation like it's like it's still like an important field. Okay? And there's some computer science people also do like simulation research. Okay? But the third one, as I said, like operating system. Okay? In operating system, there are several important branches. One of the branches is linear program. Okay, I would say, because these 3 fields, okay, I would say that probably operating system, just operating system, occupy like 50% of industrial engineering. And the inside operating system, they take probably more than about 50% or something like that. So you could say that like a quarter of industrial engineering, is about linear program. Of course, I'm not just. It is not like linear program is only for industrial engineering. So if you are into like optimization in computer science. You know, there are other like when you study like some research papers, you will find that linear programming appear in many computer science research as well. Okay, so this is an important area, okay, important problem, like across different disciplines. Okay, but used mostly probably in industrial engineering. The second most used probably is computer science. Anyway, okay, so what is linear programming? So let A be an n times n matrix. Okay, so it's and B be an n vector. Okay, so control on like the pink part. Okay, in the B. Okay, so A is an n times n matrix. The B is the pink vector, column vector. Okay, C be an n vector, the pink row vector on the right hand side. Okay. So we want to find an n vector x, okay, that maximizes CTX subject to AX smaller equal to B. So the x, the pink color vector is what we are looking for. We are looking for a solution here, okay, x that satisfies this inequality, AX small equal to B, and this x can maximize, and C, actually C is also a color vector, but we put it go as like the transpose of C, CT times x, or maximize the right hand side. So this is like the general description of linear programming. Okay, and there are many algorithms that are proposed to solve this linear programming. And among them, the most famous one, okay, in the past, when I was like a student, okay, well, the most famous one was secret algorithm, secret method. In the secret method, basically you walk through like some boundaries to find the optimal solution for this linear programming. So it is practical and it's very fast in most cases. But in the worst case scenario, it could be exponential. Okay. So at the time when I was, remember I told you I went to like NTSU, industrial engineering, right? At that time, this interior point method was just like proposed. Okay? This interior point method, okay, the important conclusion is that it guarantees it can find the optimal solution in a longer time. Okay, so it is no longer like the worst case exponential. Okay. And it competes with sequence method. Okay. The other one like it is also very practical. But the difficulty is, okay, in most of the people in industrial engineering, probably most of them will still use sequence method because sequence method is simple. Okay, so some sense it's because it's simple. Anyway, so these methods focus on solving the general linear programming problem. And yeah, I mean, this is, indeed a difficult problem to solve. And so the simplest method and the interior methods are obviously both very important contribution, okay, in industry and in computer science, in operating system, there are so many important research results based on it. But we are really not going to talk about simple methods or interior point methods today, okay? Because we are not going to cover the general case of linear programming. What we are interested in, even the feasibility problem, okay, meaning that can you find any solution, okay, for your AX small equal to B? You don't need that. You don't need that to optimize, to maximize that CTX. You don't need to maximize that. As long as we apply that, any solution satisfy this equality. Okay, so we call this feasibility problem. Even this feasibility problem is as hard as the order of the linear. So yeah, just want to give you an idea of the problem. And if we still use linear program to solve many research, optimization research problem. So this is of course, knowledge, everybody use weighted descent to solve optimization problem, but we try different approach. So what we care about today is not a general linear program. We care about is what we call a system of inference constraints. Okay? So it is the special case of linear program. Okay? Something looks like this. It is always the difference of two variables. Difference of two variables. Okay? So, for example, x1 minus x2 small equal to a certain number, blah, blah, blah. Okay? And, it is always this xj minus xi small equal to wij, this format. Okay? So if you try to, this is also the feasibility problem, in the sense that we are not in a position to maximize anything. But later on, you will find that the algorithm we propose, more like, obviously, it's going forward, right? Because we are going to use, we are talking about like education program. Okay. So the going forward algorithm actually maximize some. Okay. Clean myself. Right? So if we try to represent this thing as this form, it's going to look like your A matrix is going to have a dimension E times B y. Because this one, oh, by the way, I mean, here, I mean, we are trying to represent this one as a graph. Okay, we represent xi as bi. Okay, the negative term first, and the positive term next, and the age between them as a weight after magnitude. Okay, and in this case, we represent this as a graph, then we obviously have like ages and variances, right? So what is the n? What is n? N actually stands for the number of constraints, right? N stands for number of constraints, right? I mean, just like or put it this way. H this one times this one equal to 1 of this, right? Or smaller equal to 1 of this, right? So this one, okay. So we have how many constraints? It's like is represented by n, right? So n will represent number of constraints. So each constraint, as I mentioned, is going to be converted into age, right? Each constraint has an age, right? Each constraint has an age, right? So your n is going to be the number of ages. How about this one? The n, well, you will find most of this n, the number is 0. There are only two terms that are non-zero. One is 1, one is negative 1, right? Okay. Times this, v1 or x1, x2, blah, 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 blah. Right? So this is like, this has to be the size of the xi's, right? So now we represent each xi as a node, right? As a node. So this size is the number of nodes. Okay? So the number of nodes is like the size of V, right? So if we try to represent each of these constraints as a graph, then your matrix A will look like this. And your so I mean you might wonder, why do we want to so this graph is called constraint graph. There is a special term for this. So you may wonder, why do we want to represent this one as a constraint graph? Okay. It's the idea is like this. If the constraint graph contains a negative wave cycle, then the system of differences is unsatisfying. You will find that it has something to do with the shortest path. Why? Okay. Say we have a cycle. Okay, from V1 to V1. This is a cycle, right? And say this weight, the total weight, is negative. So now let's represent each of these age as the original constraint. It will look like this, right? It will look like this. Where x1 is your v1, x2 is your v2, and so on. So xk, the last one, go back to x1, right? Okay, and this W1 to W2 to blah 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 WK1 basically represent the weight for each of these ages. Then what happens is that so if this appear to be a subset of your constraint, you try to add up everything on the left hand side and everything on the right hand side, then you will find that something interesting happens. The left hand side, everything cancel out each other, right? Everything cancel out each other. Right hand side, as I mentioned, it is negative weight cycle, right? So this is going to be something, it's going to be weight of cycle, it's going to be something smaller than 0, right? So the 0 equal to something negative, that's impossible, right? That's impossible. So regardless of how you assign the value of variables, okay, this is impossible to satisfy, right? So no value for xi can satisfy the constraint. It's as simple as that. Okay. So first, if there's negative weight cycle, we couldn't do it. This part is identical to the assumption that we have for the L4, right? Okay. But we do allow negative weight, right? Here we do allow negative weight for H. Okay, this Wij could be negative, right? It could be negative, right? We just don't allow negative weight cycle, but some H could be negative. So obviously, like when we consider this graph, like we couldn't use like diagram, but moving forward it works. But we only have these H's. We need to have a starting node, right? We need to have a starting node. How do we convert the constraint graph into something that is more likely to be used for building forward? So suppose no negative weight cycle exists in the constraint graph. Okay, the constraints are satisfied. But satisfiable, when you say a constraint is satisfiable, how do we solve it? Okay. So the idea is like this. Say this is your constraint graph. Be careful. The constraint graph may not connect to each other. Here we try to make it connect to each other, but it is not necessarily the case. Okay? But of course, each node must have at least one edge connected, right? Otherwise, it wouldn't appear in the constraint graph, right? So we just add a new vertex S to this graph, okay, and connect each node with this node S with a 0 weight H. So we don't change anything in the original constraint graph. We just introduce a new node S, with negative weight H to connect this S to every other node in the constraint graph. Okay? So, the H we introduced, it has 0 weight, right? And it is one direction. You cannot, there's no way for any node to come back to S and go back, come back to S and go out. That's impossible. So no additional cycle is introduced, right? If you want to introduce additional cycle, S must be part of it, right? If any additional cycle is introduced, S must be part of it. If S is part of it, you must have an edge coming to S and going out of S, right? We have edges going out of S, that's true, but we don't have any edge coming into S, right? So it is impossible for this process to introduce any additional cycle. Okay? And in the original constraint graph, we may have cycle, but we don't have negative cycle, as we already mentioned earlier, right? Okay? So, in our work, the shortest path from S to any other nodes exists, right? The shortest path exists according to what we previously we talked about when we go down. So, the interesting thing is that we simply assign the shortest path, weight to xi, okay, shortest path weight from S to vi, okay, to xi. This one will solve the constraint. Okay, will solve all the constraints. So how do you do that? How do you do that? I mean, just assign okay, because each xi is represented by a vi, right? So from S to vi, we will have shortest path, right? The shortest path weight, the path weight, shortest path weight, we assign that value to xi. We solve the constraint graph. We solve the constraint, the set of the constraint equation. Okay. Why? Because remember, we have this triangle inequality. We have this triangle inequality for the shortest path. Now, the short path from S to Vj, okay, must be greater or equal to the shortest path from S to Vi, and then from Vi to Vj, right? If there's an edge between Vi and Vj, okay, then the shortest path to here, okay, it could go through here, but the shortest path weight must be greater or equal to the shortest path weight here plus Wij, right? I mean, previously we call it a triangle inequality. Okay? So we have this. Now, this one is xj, right? This one is xj. This one is xi, right? We assign this one to xj, we assign this one to xi. So in other words, well, it satisfies the constraint. Xj minus xi is smaller equal to wij, right? Okay? And this is true for every edge, for every possible edge, right? So all the constraints are satisfied if we do this assignment. If we use this one to assign the value of x to every xj, okay, in other words, we can use Bellman-Ford to solve this problem directly. Okay? So Bellman-Ford algorithm can solve a system of n difference constraints on n variables in big O n times n times. Okay? So this is like one interesting application of Bellman-Ford. Okay? And the solution that is coming out from the Bellman-Ford. Okay, I mean obviously, first it's one of the possible solutions for the feasibility problem for this for this special case of inequality. But actually, it also it also maximize. It happens to also maximize x1 plus x2 blah 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 plus x3. We also happen to maximize this subject to this all these constraints. Okay, so this is the first thing. And we also have this one. Not only maximize this, we also minimize this one. Sorry, minimize this one. And also it maximizes this one. Like all the x, the biggest one is the xi minus the smallest one in xi. Okay, the difference between these two is minimized. Okay, subject to the constraint, to this constraint. I mean, why this is the case? I leave that to the exercise for you guys to think about. Okay, and this will appear as like in the exercise next time. Okay, so just want you to consider that. So again, there's such this optimization. This is minimization. What does it have anything to do with any special application? One interesting application is DOSI layout. I know like many of you, okay, well, we are in computer science, but in Taiwan, like, a lot of students graduate from computer science, eventually, like, get into like a hardware company, okay, to do some program, so in like, chip manufacturing, there's interesting, what should I say, interesting problem. Okay, something like this. Okay, so assuming each of them, because VLSI basically it's like we are going to put a lot of like large circuits together on a board, So basically, like you can kind of imagine each of these is a complicated circuit board. I mean, on a single board. Okay. So because of the certain physical constraint, you couldn't put like this circuit boards too close. There must be certain size, certain space between them. You put that. Okay, and another question is like this. We want to minimize the total space because in Taiwan we are good at producing tiny chips, right? Tiny circuit boards. So we want to compact the space between the feature. Okay, each of these you could say it's a feature. Okay, the feature of the BOSI layer without bringing any features too close together. We have to leave some space. So this is this space, minimum space. Okay, minimum separation before that. Okay, so how do we, formulate this one into a problem? It's like this. We consider the left-hand side of each feature. Okay, say, if we use line here, and the left-hand side of each feature, we say, for the first feature, the left-hand side is x1. For the second feature, the left-hand side is x2, and so on. Okay? Then, obviously, the x2 minus x1, it will have to be the d1. The d1 is the size of the first feature crossed down. Right? So x2 minus x1 has to be greater or equal to d1 crossed down. Okay? And the same thing, x3 minus x2 will have to be greater or equal to d2 crossed down, and so on. So we have a bunch of these differences constraints. Right? We have a bunch of these differences constraints. And if you use the Bellman form to solve this difference constraint, remember it will also minimize the max xi minus the min xi. The max xi minus min xi basically represent the width of this circuit board, right? Okay, not exactly. You have to say it's the width of circuit board plus another, the last, the size of the last feature. Okay, but yeah, it's close. It's close. So Bellman form minimize this one, which compact the layout in x dimension. Of course, we may need to do that for different dimensions, okay, to make sure that we are able to compact like our VLSI, visual design. Okay, so this is like something you could, do. Okay, something you could apply the Bellman form algorithm to solve. Okay, I mean, it is a popular problem, but it is also, interesting that at least in Taiwan, I think that this must be something that considered by many hardware manufacturing companies. Okay? So that's the end of this part. And let's take 10 minutes break. We'll come back. We'll continue the discussion on the all pair shows path. Okay?
有去上课吗？啊？我昨天早上有去上课吗？
我觉得这里的人都没去哦，没有。
没有，我在睡觉。
睡觉。
我在准备公司。
我在欢乐为房。他们这种考期中都考可以，对吧？那当然好，看教学的时候知道，对吧？那其实至少还有收取。那他期末考虑，那你每个人看期末考虑。我不知道啊，干超难，超难。
真的，就还在问他，
我以前问他干嘛去吃？不走。我还有作业没提，作业没提。拜拜。我们4个还好。我操，我是这个。是6个。哎，但是现在说多少？
所以上个礼拜这么多人来，是因为要签停休单啦。哦。
现在说多少人上课吗？
不知道，线性代数没有，线性代数多一点。
到现在说使用哪种还会
多一点，但没有很多。
多一点，对。现在是大概有10个左右。
对。修课人数到49，
降到49哦。
对啊，
原本多少？
哦，80，然后第一次段考还有72，然后我前2天他还有52分，是49。
你会觉得老师作业很多吗？你会觉得老师作业很多吗？
超多，很多。我第一次知道那个什么 I love PDF 的压缩，一次只能上传20张图片。
分2次压缩的。
对，我就分2次解。对。
你可以直接装 Adobe 的一些特殊版。
对，可是就那时候就懒，我就直接线上，我把全部都删掉。
都没有，不要就是因为我的会是就是还在写，然后就记，然后想，然后。
你是图片党，图片党的图片。为什么你不直接会出错？
事麻了。
没事啦。各位加油就好。
这是我们的研究，真的假的？预防8群，对，49，有点屌。我靠，他们真的，我还有在等啊，有一个德国啊。那你也不跟他玩？对啊，那我自己也。希望死的要手。啊？没有。在外面。600个挺满的。我已经不是说写完了，是填满。
So, so this slide, this set of slide, okay, we are going to talk about four pairs showing this path from, okay, and I remember you guys also mentioned that you have learned Floyd Marshall in your data structure class. Okay. But in this class, we are not going to just talk about Floyd Marshall. Okay. So hopefully, you will learn. We will talk about Floyd Marshall, but it's going to be just a small portion of this chapter. Okay. So hopefully, you will learn something new. Oh, by the way, so I will assign the homework, the last homework, okay, next week. Okay, next week. 最后一次，6月4下个礼拜，对，对。So each homework is more than the last semester because last semester we have 6 homeworks. This semester we have 4 homeworks only. Yeah. So yes, we have more problems in homework. But supposing that we don't have more problems in total. Yeah. So anyway, that's next week. So let's recap what we have learned. Yeah, we have learned diagram. Okay, for non-negative age weight graph. Okay, the time complexity is equal to E plus E log. If we use RQ to solve this problem. And we also talk about today we talk about if you have negative weight age, okay, then you could use Roman form always, and the complexity of the Roman form always is equal to E. Okay, so these are both more like single source shows path. Solutions have, okay, and there's one additional strategy that we didn't cover is this DAG is direct acidity graph. Okay, meaning if you have a graph that does not have design any okay, it's edges are correct, but there's no loop at all. Okay, so in a DAG, okay, you could use number 4, okay, to immediately find the shortest path in P or V plus E. So how do we do that? Okay, this one I will quickly go over that here. Okay, but you may need to read additional material. By the way, did you guys have read logical sort in data structure, right? Logical sort.你们在那个资料结构里面有学过那个不是塔拉丘兽，单中后排序嘛？不好意思，我中文比较不好。 你有学过吗？副院长教吗？这个我要跟你们对齐一下，因为我不知道。好，如果是这样，if it is the case, then I can spend a bit of time, on this, and hopefully you guys can get idea. Okay. 我看有学员嘴巴张开在看我，是那个不记得，完全不记得什么东西。就说你早上起来，你会先刷洗脸，再穿内衣，再穿外衣，对不对？你不会早上起来先穿外衣再穿内衣，对不对？就是。There are certain tasks. Okay, you have to do one thing first and then the next. Okay, the task has dependency. Okay, 就是说，所谓的 DAG， 就譬如说。You're starting, okay? You're starting, okay? The preparation for the class, okay? So that's you, okay? So at the beginning, you may, attend class or starting. And then take exam, right? Right? I mean, supposedly you should study and then take exam. Right? Or is the other way wrong? or skip this part completely? I hope not. Okay. So to go for exam, maybe you need to buy some stuff, right? Like a piece of papers or like a pencil, right? Okay. Maybe you buy and then maybe that can help you to take the exam, right? Right? And this one, I mean, the stuff that you buy may also help you to, what should I say, like,有需要你可以来看，除了考试以外。我觉得比较讲，就 in general by stuff. Okay, you can use the stuff you bought. Okay, to, for example, like supposedly like 假设你买扑克牌，你可以打牌，对不对？对。Okay, so something like this. Okay, sorry, I'm not doing a very good job. Coming up with like a good example immediately. Right. It's probably difficult, but you get an idea. So basically, a lot of tasks have dependencies, right? Okay. I mean, to play, we also have some stuff, right? I mean, like poker card, like a board game, right? You do have a board game. You play it, right? Or like you play chess. You need to buy chess first, right? Okay. So basically, okay. So this stuff may end up like becoming bigger and bigger, right? And each age may also represent, may also be associated with certain weight, right? So yes. So first, this thing is what we call EAT, directed acyclic graph. Because in such a graph, there's no possible for a cycle. Okay? If you have a cycle, that means the task can never be complete, right? 如果你有一个 cycle， 你这完全没办法做，对不对？对不对？这有问题吗？应该还可以吧？这可以接受吧？对不对？如果你有 cycle， 你怎么做？做 test 1， 你 test 2， do test 2， 你 test 3， do test 3， 你 test 1。I mean, so which test do you start first? You have no way to start, right? So, and also this age may be associated with like weight. Okay. So yes, it is also okay to discuss shortest path on a DAG. Yes. Okay. So, but before we talk about like shortest path problem, we need to first talk about how do you do topological sort. Supposing that you have read from your data structure class. So I will just go over this very quickly. Basically, you just mentally select a node with no incoming edge into it. Okay. 就你从那个没有进去，没有 incoming 的 edge 那个节点，你随便选一个进来，因为只有没有那个进来的那个 edge 的，你才能够说，哎，你前面都做完，对不对？就像like this one, you only start from here, right? Because all the other nodes have dependency, but they cannot be the first node to start, right? So it has to be some node that does not have incoming edge. Okay, so you randomly pick one. Okay, after you pick one, let me just name this one. A, B, C, D, E. Okay. After you pick A, you get rid of all the outgoing edge from A. Okay. And then you continue. Okay. Because every time you pick a node without incoming edge. Okay. So for example, you pick A. So A is first, and then get rid of A, get rid of the outgoing edge. So then you could pick B or C. Again, the order is random. You don't have to pick B before C or pick C before B. So suppose you pick B first. So it becomes B. So get rid of B, get rid of the outgoing edge. Well, now you only have one node to pick because all the other E and E, they still have incoming edge. So the next node to pick is C. Okay, get rid of this one, and then you can pick E or something like that. So this is what we call topological sort or topological order. Okay, that represents the same thing. But topological sort, or we call topological order, is not unique, right? It's not unique. I mean, you could do A and then C and then B, right? Actually, you could, if you do A, C first, you could do E first, E before B, right? So there are many possible answers here, right? Okay. And how much time does it take to do topological sort? Because you need to deal with every node, right? But you also need to deal with every edge. But you don't need to deal with any node or any edge more than one time, right? Once you're done with the node or edge, they are gone. So basically, it's big O B plus E. Okay, it's big O B plus E. Okay, so now, okay, suppose, I hope by doing so, I hopefully you can recall your memory to the topological order, topological sort, a little bit, okay, from your data structure class, okay. So supposedly now you know topological sort, okay. Then, okay, how you do single source shortest path for DAT is that, okay, you try to do the relaxation, okay. So remember that. Billman 4 is not here. The only difference is that here, okay, you don't need to use this loop. You start with the same initialization. Okay, of course you don't need this. You don't need this. The only thing you need is you check is this internal the middle loop. Okay. First, get rid of the for loop. Okay. Just you only need to do this for each edge, blah blah blah. You do this. But here, okay, when you consider the edge, you consider edge from the topological order. Okay. Because each node is associated with some edges, right? So now you consider those edges, okay, not in the random order, but in the order, what should I say like that? Say you have some nodes in the topological order, right? So the first node has some edges. You consider those edges first. And then the second node in the topological order so has some outgoing edges. You consider those edges. It is here. So now, after you do this for one pass, you go through all these edges, okay, according to the topological sort, like the node that's how we sort that you are able to already find the shortest path. Let me use this one as an example. So I will cross some stuff. You can actually okay, still use A, B, C, D, E. Okay. And then, okay, say we have 10. We have 3 and negative 2. Okay, so when we initialize, just like that initialization, we have 0, infinite, for the rest of the nodes. And then we try to consider the age according to the topological order. Okay, and so the first couple age we consider are these two. Well, so this one is updated to 5. This one is updated to 2. And then, okay, here, okay, let's say we consider B first. So B, okay, according to this, will relax this infinite to 5 plus 10. So we can become 15. Okay, and then, as I said, the only node you can consider is C, because C has no the incoming edge now. There's only node that does not have any incoming edge. So you consider C, so you consider the edges, outgoing edge associated with C. So, it will be 2 plus 3 is 5. 5 is smaller than 15, so it becomes 5. And this one, 2 plus negative 2 becomes 0. How much time does it take? Because you use topological sort, so it's a B plus E, right? And then because you need to follow topological sort. So yeah, it's a B again, but then you consider every age again. So it's again B plus E. So the So you only need one pass of Milman pole. So the cost is big only plus E. For DAT, okay, for DAT graph. Okay, it's not for any graph, it's for directly acyclic graph. After all, directly acyclic graph is a very strong assumption, so that's why you could use with one pass only, you get one source shows the path. Okay. For all this. And because it's DAT, and you consider all the topological sort. Already like that. So all the possible paths from the source to all the other nodes, you already consider. So you complete like the showing path must be wrong. Okay. But now, okay, we move on from single source showing path to all pairs showing path problem. Okay. So we want to find the shortest path between any pair of nodes. So not just like one single source. So a very, very simple approach, is that if your graph has no negative weight age, okay, use diagonal algorithm many times, right? Treat every node as a starting node. Basically, just call diagonal algorithm V number of times. Okay? So doing that, the time complexity will be 15 pico E plus V log E. The whole thing times E, so it will be pico VE plus V squared log E. Okay? So this is a very simple approach. Basically just call diagonal V times. I mean, so simple, right? Not much to talk about. But this is not ideal. Okay, or put it another way. For non-native edge weight, yeah, I mean, maybe we could do that. Maybe we could do that. When how should I say that? If there's no native weight edge. But in general case, how should we do? Okay, so in this set of slides, we are going to introduce three different algorithms. So, for Floyd partial algorithm is only one. So hopefully we will learn something new from this set of slides. So first, I mean, of course, let's try to make this problem more, define this problem more formally. Okay. So the input is a directed graph. G, okay, where V is like n number of nodes, and with h weight function. Okay. So we should know each h has a weight associated with that. So the output will be an n by n matrix of shortest path length. Okay. So each position in your matrix represent the weight of the shortest path from I to j. Okay. It is aij, right? Okay, aij indicated weight of the shortest path from node I to node j. Oh, by the way, I forgot to mention so in diagram, after the completion of the algorithm, you also learn like the path, the shortest path from the source to every other node. The same can be said for Bell form. But in the pseudocode that we discussed, okay, we did not specify how you identify the shortest path. So I also want you guys to think about, okay, how you can modify the Bell form so that you can output the shortest path from the source to every other node. Okay. And same thing for open shortest path. We can also try to find out the way to output. If I want to actually complete the open shortest path, how you can give me the path from node I to node j. Okay, anyway. So the basic idea, the simple idea would be, okay, just like the diagram, okay, you just run the Bell form, once for each vertex. Okay, the complexity will be, because the only rule is algorithm, the complexity is BE, right? So when you run this B number of times, so it will be B squared, okay? And then because like in case of dense graph, your E, the size of E is pretty much like B squared. So, or let's represent E as a number of nodes, and okay, so the age is like n squared in size. So the total will be theta n to the power 4 times in the worst case. So it's pretty bad, like n to the power 4. Okay. But at least it's an intuitive approach. It's an intuitive approach. So let's try to optimize it. Okay. Let's define something like this. Okay. Let's say A to be Aij, where Aij is like the weight from node I to node j, okay, or infinite, okay, if there's no such age. Okay, so basically the Aij represents the adjacency matrix, okay. So and we define this Bijn to be way of the shortest path from I to j that uses at the most n edges. We use n edges, okay, from I to j. So now we say the Bij 0, okay, meaning you go from I to node j with 0 edge. It is 0 edge. Then it's going to be 0 if I is j, right? You just don't go anywhere. Stay there, right? The weight is 0. Okay. If I is different from j, then it's going to be, because you just have no way to reach, to go from I to j without any edge. If they are different, no. You need to go through at least one edge, right? So this definition is easy. And for n, starting from 1 to n minus 1, we can define Bijn, okay, to be mean. Sorry, like it's very nice. You get it. So Bij the mean, okay, of for all the k,我刚讲过，这个 n 就是代表你用了多少个 h， 你用多少个 h。那这是你说你前面到了 dk 的，this is I, this is j. So, okay, you use n number of edges in between I and j. Well, at most, n number of edges between I and j. So, you could consider the 1, 2. One of them must be the previous part, right? Well, 前面一号一定是弄的移动的在其中一个。And this one must be I1 then minus 1. Right? So this one is I n minus 1. And then if you have h in here, then it will be this one plus this h, the h weight. Okay? And you may have many of them. And whichever give you the smallest one is this one. We're going to assign that to here. So this is a very, very simple recursive definition. To extend one more hop. So this one should go to the top. Somehow it's all that. This is what I actually tried. This one is class ball. IK should be a subscript. This one that should be superscript. Sorry for like all that. But you get idea. So you could, implement this by this group. Because you need to consider every node. Okay. You're going to find a minimum. So this is the realization. This is the actual realization. And you do not need and we don't have no negative weight cycle. If we have negative weight cycle, then error ij will be dij n minus 1 to dij n. Okay, meaning that if you have no negative weight cycle, the path length will be at most n minus 1, right? We just mentioned about that in the Bell and Ford algorithm discussion. 就是如果说你没有negative weight cycle， 你的最长的最小路径一定是 n 减一倍的 path 的 h 对度。所以 so that's why when you reach n minus 1, I mean for when your superscript is greater than that, greater than n minus 1, they should be the same. And then represent the shortest path operation. So, having said that, we could use this to create like an algorithm. We need like another loop. Okay, basically to control the superscript. Okay, the superscript. When you do this n minus 1 process. But we could actually do it a little bit better by introducing the dimensions. Okay. I mean, the computing the dimension location. If each dimension is the size n times n, then Cij is like this, right? This is nothing new, right? Like, you can learn this from your linear algebra. I know very well because I also teach linear algebra. And the time complexity for measure multiplication is theta n cubed. If you use the standard algorithm, we know there is like if I encounter algorithm that can help you to reduce the complexity a little. But let's assume we use the standard. If you map the cross into the mean and the modification into the cross, then what happened? Okay, this one can be done. This line will become this one. So measure modification can be used to do this. Okay? And it will look much better. And if we do that, then basically we start from this. This will represent the, remember, or this is B0, this is B0, meaning, remember, what the N represents. N represents the number of ages that you use for this path. So E0 means you don't use any age, right? So if you don't use any age, you can only go, from this node back to this node. Only can stay this node. So the diagonal path is 0. So any element other than diagonal path is infinite. So we call that, and it's not exact identity matrix, but you get it. So this is D0. That's also what we define previously as okay. So if you could with this definition, okay, we could use the measure modification to deal with all pair shows pattern. So it's going to be combination modification. Okay. And D1 becomes D0 times A adjacency matrix. It will be A to the power 1. D squared, D 2. It will be D1 times A will be A squared, and so on. So D to the power N minus 1, or D, superscript N minus 1. I probably shouldn't say power N minus 1. Superscript N minus 1. It will be D superscript N minus 2 times A to the power N minus 1. Okay. So the result becomes like computing. Okay. So when you reach En minus 1, the AIJ will recall shorter path rate from one dimension. So the time complexity is going to be because each node, right, each measure multiplication is n cubed. So you need to do is like close to n times, or N minus 1 times. So it will be n times n to the power 3, so it will be n cubed, n to the power 4. But this is not any better than trivial form n times. So this is like not good enough. I mean, there are some stuff we could do to make it a little better. For example, okay, we can do like repeated squaring because we know a to the power 2k is ak times ak, so we don't need to do like it's 1 by 1 by 1. We can do like a to the power 2, a to the power 4, a to the power 8, and so on. So we can do a much faster speed. Okay. So if you design this algorithm well enough, the time complexity becomes n cubed times O. How to do this is like a very simple divide and conquer. So I'll leave that one design to you. But this is very simple algorithm to design. Okay. basically, just design an algorithm to compute a to the power n. It's very simple. And if you want to check negative weight, like just check the diagonal or negative value, repeat all the additional time. We can play with that. Okay. This is kind of similar to what we do for the random walk. Okay. So this NQ log a little better than calling level 4 like n number of times. But there are other ways to do this. But I think we are running out of time. So we will stop this here today. Next time we'll start from float washing, which should be done quickly. But we have additional method to cover. So next time I hope to finish this self-slide and cover something else. Okay. And then we have like how many? 3 more lectures, right? Excluding today, we have 3 more lectures. So next week we will finish this lecture, this slide and one more stuff. And I hope we will be able to cover 4 more topics. 4 more topics. Okay. Well, not for this week. Okay. So that's my plan. So yeah. Any question? If no question, that's it for today, and I will see you next week. Okay? And remember that I will give out the homework for next week. Okay? And this homework 3 is extended for 3 more days. I announced it like previously, but you guys, some of you didn't come until like later. So just want you guys to be aware of that. Okay?